magical world of fluids. I'm your host, Visk Reynolds. This is a golf ball, 1.68 inches in diameter, approximately 350 dimples. Today, we'll be examining why golf balls have these dimples. This diagram shows the phenomenon we wish to examine in the lab. As you can see, the dimpled ball has a smaller separation wake, thereby decreasing the pressure drag on the sphere. To examine this behavior, a model golf ball was fixed inside of a water channel with adequate dimensions such that wall drag could be neglected. A pump was used to alter flow velocity, and a dye injection needle along with a high-speed camera was used to observe the unsteady streak lines. To correlate pump frequency to Reynolds number values, this calibration chart was used in conjunction with the given equation. Reynolds number equals density over viscosity of water times flow velocity times a characteristic length. The characteristic length was chosen to be the diameter of the sphere, shown here to be at 3/4 scale of an actual golf ball. The limitations of our water channel allowed us to study Reynolds number regimes at a low value of 2500 and a high value of 15,400. The first visualization you will see is the smooth ball at a Reynolds number of 2500. Notice the separation point labeled by the white dot. The location of the separation point determines the size of the separation wake, which accounts for the amount of pressure drag on the sphere. The second case is identical to the first, this time using the dimpled sphere. As you can see, the separation point and wake size are similar. This is expected because we are still operating in the laminar flow regime. Now we will study the turbulent case. Remember the difference in flow shape we expect to see from the smooth ball to the dimpled ball. We expect the dimpled ball to have a smaller separation wake. The first turbulent case is the smooth sphere at a Reynolds number of 15,400. As you can see, the flow is much faster, and we have again labeled the separation point. The final case is the dimpled sphere at a Reynolds number of 15,400. From what we expected to see, this is rather curious. You may have noticed that there was not a significant difference in the flow between the smooth case and the dimpled case. To solve this conundrum, we consulted our panel of experts. Esteemed graduate students from the University of Utah performed dimensional analysis to evaluate the validity of our experiment. In order for our model to properly simulate an actual golf ball in flight, we would have to match the non-dimensional Reynolds numbers to achieve dynamic similarity. An actual golf ball in flight experiences Reynolds numbers of approximately 100,000. To achieve this in our experiment, we would have to operate at a velocity of 3.16 meters per second. The maximum velocity in our water channel is only 0.49 meters per second. This is much too slow. Proper results would require a faster water channel or perhaps a wind tunnel. So remember, children, when performing experiments in the lab, be sure to do your math first so you can get usable results. We hope you've enjoyed another magical evening of fluids. Now next time you're on the golf course, you can fascinate your friends with all you've learned. We'll see you next time.